Hello and welcome to another Ford and GM transmission video. This one is going to focus on the electrical operation. So first, let's look at the electronic system as a whole. I made this little flow chart to kind of show what the inputs to the TCM are and what the outputs that the TCM controls. We're actually going to look at all these different inputs and kind of describe their functionality. We're going to look at some of the strategy, what the TCM does, and we're going to look at all these different outputs and see how they control the transmission operation. So to start, let's look at a couple wiring schematics to kind of understand how this thing is wired up and how it's controlled electrically. We've got a couple power supplies right here feeding 12 volts into our TCM. We've got a ground, and this is communication from the instrument cluster. Now we get into some vital inputs. We've got a park position sensor, a 2-switch position sensor. We'll cover that later in this presentation. These 4 are speed sensors, and these 4 speed sensors operate in the same fashion. They receive 9 volts from the TCM, and they alter current flow in those circuits depending on a toothed wheel, and we'll see all that stuff coming up here in a second. And that's going to send a signal back to the TCM on the speed of our output speed, our input speed, and then 2 intermediate speed sensors. We've got our range control valve. Now this works closely with this 2-switch park switch assembly, and this basically monitors the position of the valve, and then this monitors the position of the actual actuator that shifts us in and out of park, and then we have a temp sensor. So these are our main inputs that we have on this transmission. And then the TCM uses those inputs to determine what to do with these solenoids, or these output components. You can see I've got my 6 solenoids here. Those are the ones responsible for the clutches. Matter of fact, if you look at that kind of that identification there at the top where it has A, B, C, D, E, and F, those are the clutches that they operate. And just to confuse you, they don't call it that. They call it valve 1, valve 2, valve 3, valve 4, but they do go up in an increment, 1, 2, 3, 4, 5, 6, A, B, C, D, E, and F. And they're about 5 ohms apiece. And then over here, we've got valve 9, and this valve 9 is that default disable valve. The resistance of that is around 20 ohms, and the resistance of these pulse width modulated solenoids is around 5.4 ohms. Much lower ohms because most pulse width modulated solenoids are going to be low resistance, create a big, strong magnetic field. But they are powered by the TCM, and then the ground is provided also by the TCM, and you can see these are all pulse width modulated. And then we have a couple more outputs, the auxiliary oil pump. We'll look at that. If you saw the rebuild video, we talked about that a little bit as well. But these other valves, we got 7 and 8. That's our torque converter clutch and our line pressure solenoid. And then this is a park lock actuator solenoid. The park lock actuator solenoid is about 20 ohms. And what it does is it holds you out of park once we physically move that parking pawl released. And then they want this obviously released. They put a little pin in there and lock this transmission out of park. You might have noticed on your scan tools where you see high side driver 1, high side driver 2. That's where this kind of comes into play. Our high side driver is that power switch. You can see in this case, the high side driver is going to turn around and feed these 3 solenoids and the auxiliary oil pump with power, and the other high side driver is going to power up the other solenoids that we had on the previous wiring schematic. Now this schematic looks pretty similar to the second schematic that we looked at a little earlier because it's got all these speed sensors, but what we're really focusing on here is this range sensor, and that range sensor operates a little bit differently than your traditional range sensor. It's got 4 wires here, it's got power and ground, and then these 2 output sensor signal circuits, they're going to output a duty cycle. In this case with the General Motors, one of those signals goes to the engine control module and the other one goes to the transmission control module. On Ford, they send them both to the powertrain control module. They kind of work as redundant circuits, but they do actually operate differently. And we'll see when we cover the range sensor section in this video how they operate, but it's pretty neat because as the duty cycle changes on one, the other changes in the opposite direction. Now let's talk about these speed sensors. These speed sensors are a little bit unique. They are 2-wire sensors, and a lot of times you've been around for a while, you're like, a 2-wire sensor, it probably generates its own power, a variable reluctance type sensor or inductive sensor. That's not how these things work. They are more like the advanced wheel speed sensors that you see on vehicles now. The 2 wires, you got one that's power and one that's a signal circuit. And if you hook up a scope to it, a lot of times you'll just see a steady flat line, and even if you're spinning parts, you just won't see a pattern. Because what the sensor does, it actually toggles a power supply on and off in here. and you really don't see the voltage change, but what it does is it adds current. So and we're talking milliamps, like 7 milliamps is what it's changing. Now these are smart sensors. They've actually got little computer chips in there, and there's multiple sensors in each one of these. So that way they can measure rotation. Imagine if I've got 3 sensors in a row, and I've got a tooth or a window that's passing the sensors in this direction, they're going to toggle 1, 2, 3. And if the tooth is passing in that direction, it's going to toggle 1, 2, 3. So it can look at the order in which these internal sensors toggle, the ones that are in here, and then that informs a little computer chip in there to send an output signal. So we're not actually directly measuring the tooth. It's being interpreted by the internals in the sensor, and it's outputting a signal. And you'll see that here in a second. Now, depending on the design, these speed sensors might be reading the windows or the edges of these windows, like they do on intermediate speed sensor 2 and also on the output speed sensor. They could also be reading off of these magnets that are embedded into the outer ring of this P2 carrier. And that actually measures input shaft speed. Or they could be measuring the tooth wheel, like we've got on this P1 internal gear. Regardless of where they're at and what they're measuring, they all operate pretty much in the same fashion. This guy right here is going to explain how they operate and what they look like on a scope. I've got all of these speed sensors wired up here on this transmission. So they're all powered up by a 9-volt battery. I've got the positive lead going into the positive side, all 4 speed sensors, and on the ground side, I've got them all grounded to the ground side of this 9-volt battery, but I put a tiny little resistor, a 220 ohm resistor, it could be a 100 ohm resistor, in line with the ground circuit. Could also have done it on the power side, but I did it on the ground side. So what I'm going to do is measure the voltage drop. I'm going to actually connect between the sensor and this resistor and hook the ground up to ground. And what that's going to do is it's going to measure the voltage drop across this tiny little resistor. And you might ask, why am I going through that? It's because these smart, I'll call them smart speed sensors, or these advanced speed sensors, they're tiny little computers in themselves. They've got a chip in there. They've actually got like 3 Hall effect sensors in there because they can tell not only rotation speed, but they can tell direction. So these things, when you put 9 volts to them and you try to capture that with the scope, you just have 2 wires to each one, power and ground, you hardly see any kind of influence on that line at all. Because what that sensor is doing is every time a tooth passes that sensor or a window passes that sensor, it ends up triggering an extra power supply in the sensor. So it changes the current flow through the sensor. And we're talking a milliamp change. So this thing only changes the current flow between 7 and 14 milliamps. I mean, it's very minimal, the amount that it changes. So we really don't get to see that just by checking the voltage. But if I put a resistor in line and I measure the voltage drop across a resistor, so this resistor is not enough to really affect the overall current flow through that circuit, but it's enough to create a voltage drop. So I can actually check across this resistor with a scope and see the pattern. So what I've got up here, like I said, I've got all of my speed sensors wired in, and power going to the power side, ground going to ground with the resistor in line, and I'm checking with a scope between the resistor and the sensor. Now if I just rotate this in one direction and then back, and it looks pretty consistent. It's like, okay, I see all these different pulses, and these are the 4 speed sensors. We've got an input speed sensor, 2 intermediate speed sensors, and an output speed sensor. Now you're like, all right, well, how does this thing measure direction? How does this pulse thing actually work? So I'm going to try to zoom in on a spot where we can see every little pulse there. Now if you look, all these pulse widths seem to be about the same width, and if I were to measure that, just any old pulse, just go ahead and measure this channel C, and we'll see that the pulse width is, it's not on there very good, but about 163 microseconds. That's what that pulse is. And you can see that is when I rotate it in one direction. I think that might have been when I went clockwise. Now I'm going to drag this zoom window all the way over where you can tell I started rotating in the opposite direction. So I haven't changed any of my settings. Maybe I can get it to a point where we can see all of them up there again. Either way, you can see they're all pulsing at about the same rate. Well, instead of trying to get them all on there, you can see they're all the pulses are about the same size. Now, when I actually go through and measure the pulse width, instead of 165 microseconds, And I haven't changed the zoom, so this is the same as it was when I did before. So you can visibly see their different pulse width. That's 48, roughly 50 milliseconds. So the size of the pulse changed. When we're rotating one direction, it sends one pulse out per tooth or per window, but when I rotate the other direction, it sends one pulse out per tooth per window, but it is a much narrower pulse. So the computer can interpret, not only count the pulses, but it can look at the width of that pulse to determine the direction. It's a smart sensor. They've got 3 sensors in one sensor body, and then depending on the order of those sensors being triggered, is going to determine the direction. It's kind of a mess of wires that I've got here, so I know this is probably a little too much to look at, especially on the video screen, and you really don't need to measure all 4 at once. I just wanted to show how all 4 interact and how they show the rotation. So I realized that was kind of a mess of wiring, so I got all that stuff out of there and kind of peeled it away with an attempt to simple this down so you can see how I have it wired up with just one sensor. So here's the 9-volt battery. You can see it powers up. Right here on this one, it's a red wire that goes into the sensor. And then, as I mentioned before, the sensor just receives 9 volts and ground. So the ground wire comes out, and here's that resistor. A little blue resistor there. That's 220 ohms, could be 100 ohms. And then that follows its way back through a jumper wire, right back to the battery negative. So now what I'm going to do is I am going to hook up my power to the resistor, or it should say between the resistor and the sensor. So here's the sensor, there's a resistor. So my signal wire, my scope lead is hooked up to, my signal lead is hooked up between the resistor and the sensor. And then I'm going to hook up to my ground. Sorry, I don't have a black alligator clip there. Kind of messing around with the colors there a little bit. So we've got our scope is going to pick up the voltage drop across this resistor. The more current that flows, the greater the voltage drop right here. The less current that flows, the less voltage drop. So what I'm doing is I'm using this resistor to force a voltage drop across that resistance. It's only 220 ohms, and the amount of current that this circuit delivers is very small. It's like, I mean, let's just say 10 milliamps, just to kind of generalize it or round it off. So this 220 ohm resistor won't really affect the operation of the sensor as we go through and test it. So I'm going to do like I did before. I'm going to rotate the output shaft in one direction, and this, I guess it'll be counterclockwise, and then clockwise. You can see I got my signal here, and just as before, not spend too much time talking about this, but you'll be able to see the pulse width change. So that's my pulse width right there. And I'm going to drag my zoom window over to when I rotate it the other direction. And you'll see the pulse width is about 1/3 of what it was going the other direction. That's how they determine direction. Every one of those pulses is a window or a tooth. So in this example, I picked the P2 planet, and I did that on purpose because it's kind of unique. It's got these magnets attached to the outside of this carrier. And it's part of the input shaft. The input shaft splines to this, so when the input shaft is spinning, it's taking this P2 carrier with it, and it's spinning these magnets. Now, the speed sensor that is going to be measuring that has to measure it through that clutch container drum assembly. But it can do that, and it's sensitive enough where it can pick that up. So every time a magnet passes that sensor, it triggers a pulse. And depending on the direction of the rotation of this part, it triggers either a narrow pulse or a wide pulse. There's no doubt using a scope and a little resistor, 9-volt battery, and actually seeing the actual change through voltage drop across that resistor, it shows a much better picture, gives you a better indication whether that sensor is working properly. You can also go through and see if you've made, like on that P2 planet, if you spin that around, you can see if you're going to be missing some pulses because of maybe a damaged magnet. Now this guy is going to talk about these speed sensors, what they're measuring, and where they're located in the transmission. So the 4 speed sensors that we have measure these components. This first speed sensor is our intermediate speed sensor 1. It measures off of the P1 internal gear, off those teeth. It has 50 teeth. Our second speed sensor is the input shaft, or the turbine shaft speed sensor, and it measures off of the P2 carrier, and the P2 carrier has 40 magnets embedded on the outside of it. This third sensor right here measures right off of this clutch container, and that'll be considered the intermediate speed sensor number 2, and it's got 50 little windows in that intermediate speed sensor that it can read off of. And lastly, we have our output shaft speed sensor, and the output shaft speed sensor measures these windows that are attached to the parking pole assembly. That measures our output shaft. There's 60 windows around that output shaft. So looking at these components on a bench, the intermediate speed sensor 1 is going to pick up on this P1 internal gear, and there are 50 teeth on the outside of this internal gear. Now this second sensor is the input shaft or turbine shaft speed sensor, and it measures off of this P2 carrier where they embed the magnets on the outside of this carrier assembly. And there are 40 magnets embedded into that ring around the outside of this carrier. The next speed sensor is the intermediate speed sensor number 2, and that measures these windows that we've got around the outside of this clutch container. There are 50 windows in that steel ring that's pressed onto that clutch container. And that clutch container houses or splines that P4 internal gear assembly and the P1 carrier. Last but not least, we've got the output carrier, and that output carrier is the output for the transmission, and our output speed sensor picks up on these windows right here. And there are 60 windows attached to this metal ring that's welded to this carrier assembly. So now you know where these speed sensors are located and what part they're actually measuring in the transmission. And when we refer to scan data, we'll see all 4 speed sensors listed. And we'll also see, we'll see a RPM PID, we'll see a direction PID, but it's kind of interesting. You see here it says unknown, has a direction signal, say about 0.04 of a millisecond. And they do that for all 4 of those speed sensors. So not certain why they say unknown. When it's pretty obvious, they can tell which direction these are going. Maybe they're not using that information, even though the sensor has the ability of providing it. But on this little movie here, we see some of the scan data that's available that'll help us diagnose these speed sensor issues. In this case here, you can see I've got my engine running. So my input shaft speed sensor is picking up engine RPM. Now you can see my output speed sensors running. These are the 2 intermediate. I'm cycling up through the gears. This is being operated on a lift right now, so things go pretty quick. And you can monitor and watch your RPM changing. As we get up to 7th gear, you can see we're in 6th, 7th, boom, we see that jump up in RPM. We'll see when we shift to 8th, jumps up another, I don't know, 1400 RPM. So these are the sensors that are providing information to the TCM on when the transmission shifts, how long the shift's taken. So as you can see on our scan data, we actually have a decent amount of information that we can use to help diagnose speed sensor related issues. So now jumping over to the range sensor. This range sensor operates kind of in a unique fashion, and they've got 4 wires, power and ground, and then these 2 signal circuits. And these are the duty cycles of the 2 signal circuits. And based off of our range, park, reverse, neutral, drive, and low, each sensor is going to output a specific pulse width or duty cycle. In this case, you can see park is, I'm going to say around 15, and then reverse is around 45, neutral is around 60, drive is around 75, and low is around 85. Now if you look at range sensor 2, it's like the inverse of that. So where we had 15% over here, we'll have 85% there. And where we had 45% here, we'll have 55 here. Where we had 60, we'll have 40. So I can go right down the list. If you added signal 1 to signal 2, you'll get about 100%. Now, as I mentioned, Ford does do it a little differently. They use a powertrain control module instead of an independent ECM and TCM. Now, in their diesel models, they apparently have a TCM. But yeah, so you've got your range sensor circuit here, and you can see they send both signals to the PCM. Whereas General Motors, here's our range sensor, receives power and ground from the ECM, but sends one signal out to the ECM, and the other signal goes down to the TCM. On the scan tool, we got valuable information as far as our range sensor is concerned. You can see as I switch between my different gear selections, you can see the duty cycle change. It lets me know about my 9-volt reference circuit power. And when I go into manual range, I can actually go through and push the buttons. This is on the column shift on a pickup truck to ensure that those switches can read properly. So our scan data does a pretty good job of evaluating that circuit. If something's wrong, I got to go in and diagnose it internally. This guy right here can show you how they function on the inside of the transmission. So after reviewing the electrical schematic, the operation of it got me curious, as these things often do. So I wanted to prove out the circuit. I'm actually going to wire this thing up just like it shows in the wiring schematic, and I'm going to measure these two signal wires to see what they output. This circuit's not that complicated. These two outer circuits is power and ground. So I've got my power lead here, my ground lead there, and then these two inner circuits are those signal wires. So I got my handy 9-volt battery system here, and I'm just going to provide power. Should probably have a fuse on these, but honestly, how much trouble could you possibly get into with a 9-volt battery, right? So that's power and ground. So right now the sensor should be powered up. So I'm going to go ahead and see just what we're getting on these signal wires with the scope. And I'll hook this up to ground. This is a simple Pico 2204A, nothing fancy. And what you see here is nothing. So when I first did this, I was like, what is going on? Shouldn't I getting be a pulse width modulated signal out of this based off of the range position of this switch? Then I thought maybe this operates similar to the GM mass airflow sensor, where yes, they have a frequency, but the mass airflow sensor provides a ground for a voltage that's supplied by the ECM. So in this case, maybe the voltage is supplied by the TCM or ECM, depending on who's doing the job, whether it's Ford or GM. And maybe this sensor just toggles the ground. So I'm going to wire it up in that fashion. That's where these two resistors come into play. I'm going to tie these into my power, kind of share it with my sensor wiring. Then I'm going to take these signal wires and I'm going to hook up the signal wire to that circuit after the resistor. So what I've got now is 9 volts going through a resistor, 10,000 ohm resistor, and back into the sensor, into the signal circuit. We'll see what kind of a pattern we get then. We'll do that to both of them. And voila, as you can see now, we get a pattern. Now with this trigger in place, we can see a nice steady pulse width modulated pattern that changes its duty cycle based off of the position of this range switch. And the way Ford explains it, if you add the duty cycle of A to the duty cycle of B, it should equal about 100%. As I move this range sensor, you can see they kind of trade off. If one has a long duty cycle, the other has a shorter duty cycle. So right now A has a short duty cycle, B has a long duty cycle. Move my range sensor over. Now A has a long duty cycle, B has a short duty cycle. So if you do a math channel and you say positive duty cycle A plus positive duty cycle B, if you take a look, it's right there. Let me put my little cursor. Bounces around a little bit, but pretty close to 100%. Here I'm moving my range sensor around. You can see them changing. If we add the duty cycle of A and B together, looking pretty close to 100% to me. So this could be just about redundancy like Ford uses it, but General Motors, they go ahead and send one signal to the TCM and one signal to the PCM. No matter how they're using it, I still think it's kind of cool to see how that they're using the pulse width modulation and duty cycle to determine the range position. And as we saw on the scan data, how a certain percentage of duty cycle is going to relate to a certain range. Now mind you, I understand that this is not a check that somebody's going to do in the shop. For some reason, if you really did want to bench test this, maybe you're running into some kind of a weird issue and you wanted to validate these parts are good, you can't do it. You can't bench test it. But by all means, I would never expect anybody to go through and do all these little electrical tests These are really more for my curiosity more than anything. And now we're going to look at the park system. And as far as the inputs are concerned, we have a park valve position sensor, and we also have a park actuator position sensor. Right here you see this is an auxiliary valve body off of the second generation General Motors unit. And this sensor right here, as I'll show you in a second, is a little mini Hall effect sensor that's going to determine whether or not this valve stroked. So if your transmission has the ETRS, which is also known as the Electronic Transmission Range Selection System, you're going to have this extra valve body up top. You're going to have a default disable solenoid, and you're also going to have this sensor right here that's going to monitor the position of this valve. It might be called the ETRS valve. It might be called the park control valve, but either way, this sensor is going to make sure that this valve strokes, and that's going to ensure that this valve moved to deliver hydraulic pressure to the park actuator, which also has a couple sensors. Now the way that I can go through and check this is very similar to the way I check the speed sensors. I'm going to deliver power into, in this case it's this pin right here, just a simple 2-pin circuit, and I got my trusty 9-volt power supply here. So I got power going to it, and I got ground. And this is a magnetoresistive or a Hall effect sensor type circuit. So they're going to monitor the current, the computer is going to monitor the current flow through this. So in order to check this, I am actually going to tie in this resistor in line. Bring my fingers to work. So the resistor is in line with this ground circuit. And I'm hooking up my scope, as you can see, between the sensor and the resistor. Hook my ground back up. Got my finger. And then I can hook up my scope ground also. So at this point, I'm actually reading some voltage. Now this voltage that I'm getting here is not necessarily the voltage that the computer is going to see when this is all operating. This is the voltage drop across this resistor. Now when I cycle this valve and I actually move the magnet that's basically attached to the end of this valve, and I move it into the sensor circuit area here, it's going to toggle the voltage. It's going to kick on an extra power supply in the sensor, and because I've got extra power coming through that circuit, it's going to deliver me more voltage drop across this resistor. That's the kind of the concept behind it. Now these voltage values, you shouldn't necessarily expect these voltage values on like a scan tool or anything like that. Obviously I'm powering this thing up with a 9-volt battery, dropping through a 220 ohm resistor. So it is receiving 9 volts from the computer, but who knows what kind of resistance it's dropping. And for the most part, these things are looking at the current flow. We're just forcing the change in current flow is going to force a change in voltage drop across that resistor. So when I push on this valve, you're going to notice that the voltage is going to jump from where it's at now, which is about 1.3 volts, and it's going to jump to about 3 volts. So as this valve moves back and forth, the computer, the TCM, has the ability to ensure that that valve actually stroked. When this valve strokes, like I said, it's going to deliver line pressure to that actuator, the park actuator, to actually physically move the actuator and move the shift mechanism into park. So that auxiliary valve body was like the first part of this 2-part system in order to get this park actuator system to work. Now the second stage of that is going to be the actual actuator, and they do have a position sensor circuit there, actually 2 circuits that are going to determine whether the actuator physically moved, and he's going to explain it, hopefully really well. So if your transmission has a hydraulically actuated park mechanism, it's going to have a solenoid and it's going to have this sensor assembly. That sensor assembly is going to measure whether that park valve that is going to end up moving the park actuator into position, it's going to measure if it actually moved far enough. So they got a magnet at the tip of this park actuator valve. And when that magnet crosses through inside this park actuator, it's going to toggle these 2 switches. There's 3 circuits. There's a power circuit and then 2 signal circuits. So these are going to switch. So these are just magnetoresistive type switches. So kind of like the speed sensor, when we go through and check this, we're going to be checking it for current flow. And just like the speed sensors, you see how I have it wired up here. I've got these 2 dropping resistors. This one's for, or one for each circuit. They're 220 ohms apiece. And I'm measuring between the sensor and the resistor. Now if you watch, when I go and move this park valve over, you'll actually see the voltage toggle on those two circuits. And they could see both of those, so they could see how far the actual park lock actuator moved. So knowing the results from these two sensors, they can tell whether or not this transmission actually achieved park. Pretty smart. That is a pretty advanced system. When you think about it, all that just to get you in and out of park. Now, once again, I want to mention that not all transmissions have that. These 10-speed transmissions, they come in various configurations, and you might not have the hydraulically actuated park system in there, but if you do, those are the components that make it work. And now continuing on with the inputs, looking at the part that really hasn't changed operation over the years. This is the transmission fluid temp sensor. It's just mounted in the valve body, kind of rotate it and click it in place on the top of the valve body, measures the temperature of the fluid. As you can see on this chart, it's a negative temperature coefficient. As the temperature rises, the resistance drops. Now that's about it for the input. So hopefully you understand what's going on as far as the input information that's being fed to the transmission control module. Based off of that information, the TCM is going to operate these solenoids. And these first 6 solenoids are clutch solenoids. You can see solenoids 1, 2, 3, 4, 5, 6. That's a lot of times how you see them labeled in the wiring schematics and in the pinouts, but they kind of go in order as far as the clutch in alphabetical order. Solenoid 7 is our line pressure control, solenoid 8 is our torque converter clutch control, and then solenoid is our park lock actuator. That's the mechanism that pins down and locks the park actuator, if you have that system, in the out of park position. Now the way the solenoids operate are fairly straightforward. I've got shift solenoid A, B, C, D, E, and F. Like I said, they might be labeled 1, 2, 3, 4, 5, 6. And the shift solenoid is a direct acting solenoid. So it operates by pushing on the valve assembly itself. It's a linear type solenoid. And depending on when clutch A needs to be on, that solenoid will be turned on. So if the solenoid's off, hydraulically the clutch is off. If the solenoid's on, hydraulically the clutch is being actuated. Now the default disable solenoid is going to be related to the park operation. So that's the reason why in park you see that solenoid off, but in every other situation that solenoid is on. Now the TCM is going to control the solenoids in this transmission. These solenoids are pulse width modulated, and in the case of the shift solenoids, they are direct acting. They're called linear solenoids because they have a pintle there that physically pushes on the valve that controls their respective clutch. So to go into a little further depth, we're going to go through and look at what this guy has to say. So my curiosity got the best of me, and I wanted to see if I could operate these solenoids just like the computer does, and just like I did with that range sensor to kind of prove it out. And as I saw on the vehicle, that they operated just over 3,000 hertz. So I took my trusty little homemade PWM box, and this allows me to change the duty cycle right here and the frequency right there. And then the switch gives me different ranges of frequencies that I can operate at. And what I did is I wired up my own little coil driver. So this is going to be the frequency and duty cycle controlling a transistor or a MOSFET, and that's going to operate power to this solenoid assembly. I've been rigged up this little test device here. It's really high tech. And what it does is it has this little spring-a-majiggy on there. See that? Pretty fancy. And that's going to push on that pintle. And the only reason why I'm doing that is so I can prove to you guys that this thing, as we change the duty cycle, is going to be able to move this in and out. This took like 10 minutes to build, so just for you guys. Now I just have a little breadboard operating this, and here's a little MOSFET. So that first pin on this MOSFET is the gate. That's where my input comes in from my little frequency box, going through a resistor, I think it's just 100 ohms, and that goes into the gate. And the center terminal is the drain, so that's hooked up over here to a ground circuit. And then the last terminal on this side is the source. So what I have for the source is I got 12 volts from my 9-volt battery coming in to the solenoid, and then out of the solenoid I go into my source. And then when this is activated, when this MOSFET is activated, it's going to provide a ground to the drain to battery ground. So as far as this scope, right now it's measuring the frequency of this box, but once I hook the battery up, this is actually going to be measuring the actual frequency of the source, which is the negative side of the coil, and it's going to be triggering it to ground, and that's how the solenoid is going to be operating. Now, mind you, this is operating off of just a little 9-volt battery. These would obviously run at a much higher voltage, not much higher, but 12 volts in a vehicle. So right now we got, let's say, about a 50% duty cycle. You can see there's nothing going on with that spring. As I lower my duty cycle, you're going to see the current is going to be flowing more because it's a ground-controlled solenoid. And you can see I'm pushing that baby out. 5%, that's pretty much all the way out. Whoop. Whoop. So it's linear because I can put it partially out there, a little further. I can pull it back, a little further out, pull it back. So I got a lot of control over this, even with my little homespun electronic setup right there. So as I mentioned before, nobody's going to be going through and doing these little kind of self-tests, but it does show that you can go through and bench check these things if you have some simple componentry. I mean, that scope is $150, and I made this thing off of a simple little schematic, so I've probably got $5 or maybe $10 worth of stuff into this box. So if for some reason you got a lot of time on your hands like I do, you can actually go through and test some of these things, but I'm just doing it for the experiment's sake and for learning. Yeah, this guy does have a little bit of extra time on his hands if he's making all this stuff. But I will say that these solenoids are pretty fine-tuned, and even though this seems to be easy to control this thing on and off and so forth, realize that since they go through the effort of putting those band numbers on there, and you actually have to enter into through a scan tool into the TCM solenoid characterization, it just goes to show you how detailed and how precise those solenoids actually are. So going through and doing a test like this isn't necessarily going to probably say that, oh, this is good or this is bad, unless it's failed just completely outright. Now, as far as the scan data is concerned, we actually do get a decent amount of information from our scan data on what the TCM is doing to analyze the circuit and to check to see if electrically this thing's working okay. You can see we've got amperage command, they've got some low voltage, open circuit testing, some high side testing, and this little video just pretty much shows the transmission going through a variety of different gears and what you might see as far as changes. So this is actually the vehicle that's on a lift running through the different gears. You can see there's my gear command, that's line pressure. Now line pressure, solenoid 7 is line, solenoid 8 is torque converter clutch, but you'll see when this thing hits third gear, our torque converter clutch is going to jump up. They pretty much apply the torque converter clutch in third, leave it on, and then they start disengaging it on the downshift. But one thing you might notice is our current command actually goes higher in the higher gears, is because you have the more the current that you apply, the lower the line pressure. The less current, the higher the line pressure. This is a inversely proportional or a normally high solenoid. So you can see in 9th and 10th gear, they actually have that pretty high amperage because they don't need much line pressure when you're in these high gears. But when you're in lower gears, you get more torque multiplication. You're going to have a little bit more pressure needed to hold these clutches from slipping. But you can see in this case, we're in 10th, torque converter clutch is on, and we're running at pretty low line pressure. And of course, that's being operated on a lift. Now in this screenshot, we're seeing the same thing. I'm operating this vehicle on the lift, and there's our gear. That's the pressure that's being commanded as far as line pressure is concerned. And these are my clutch solenoids. You can see I just shifted in a second. And my line pressure solenoid, my torque converter clutch solenoid, and solenoid 8 is my inhibit solenoid, and 9 is my park lock actuator. I'm in 5th gear, torque converter clutch is applied, and like I said, you could see it switch between very low amperage to about 1.1 when they're regulating this clutch completely on. During the shift, it'll float around 2/10, 3/10, and off is off pretty much, and on is about 1.1 amps. You can see my calculated line pressure is much lower in 10th gear than it was in the lower ranges. So that's a little over 60 psi right there, so that's not even very high. So I was getting really curious on how this thing operates. So on this side, I've got the electrical pulse width modulation for our 6 clutches, A, B, C, D, E, and F. And we can see that compared to the commanded pressures for our clutches, A, B, C, D, E, and F. And I know this looks like a block. It's because it's operating at such a high frequency. These things are shuttling on and off at such a high rate that it's filling this computer screen in as a block. So when this thing's actually shifting, we're going second, third. When you see these pulses change, you see a little bit of a white show up like we just did in the purple channel there. That's actually a shift occurring. That solenoid's doing some work. Just happened there in that gold and purple again. And when you see these pressures change over here, you can see the influence on the solenoid operation and how they change the pulse width modulation. One takeaway, which I found is interesting, is when we look at scan data and we see pressures change up and down, and we know how these solenoids work through pulse width modulation, it's sometimes easy just to think, oh, they're just changing the duty cycle. Well, when you start zooming into these solenoid patterns, it's really impressive to see the control that goes on. I know this looks, like I said, like a big block of red, but when we start zooming in and zooming in, you can see that these little intermittent sections of pulsing, and they are changing the duty cycle from like hardly on to on, then hardly off. So it's almost, and they're doing it at such a high rate, at such a high frequency, it's almost like they just got a little finger kind of tapping on the end of that valve. And at such a high frequency, it's happening to the point where that valve's not physically moving from it, but it's just getting nudged a little harder or a little softer. It's very impressive though when you start zooming in and seeing how they control these solenoids. So as you can imagine, the operation of these solenoids are so critical to the operation of the transmission because this is a clutch-to-clutch or a synchronous type transmission. So as they are applying a clutch, they're releasing a clutch, and they have to do so in harmony or else you're going to get a weird shift. So the TCM is going to control that clutch feel and the clutch apply through changing the pulse width modulation on those solenoids. And the TCM is going to have to learn the characteristics of these solenoids to kind of get a head start at trying to adapt so that these shifts will be quality. And whenever you go through and you change the TCM, the valve body, the solenoids, or the whole transmission assembly, you need to go through and do this characterization or update the TCM or PCM with the solenoid information. Now jumping over to the auxiliary oil pump. Not all of these units have an auxiliary oil pump, but the ones that do, they are there to provide some volume of fluid while the engine is off when you're in this start-stop mode that most of these vehicles have nowadays. And the idea is if you keep the fluid circuits filled with a volume of fluids, you don't have any air in there, that as soon as the engine starts, the oil pump's going to generate pressure, and because it doesn't have to deliver any volume at that point, because it's already, these fluid circuits are already filled, that pressure just jumps up immediately and you're good to go. So I was curious, a couple things. How do these things operate and what kind of pressures do they generate? So electrically, this auxiliary oil pump, it's got, on this connector, it's got 2 powers coming in on the top on the outside terminals, and it's got a ground and it's got a signal circuit. The signal is actually, it receives from the TCM. When it receives a 100 hertz signal, you can see I got the frequency down there. And then this right here is the duty cycle. So it receives a 100 hertz signal, which it kind of accepts and approves. And then based off of the duty cycle is going to be a command on what the RPM is supposed to be. And I did this in the overhaul video. I simulated the power, simulated the signal, and the pump kicked on and ran. Everything worked great. On this video here, I wanted to go through and see if this had the ability of generating any pressure. So I went through and filled the pan with oil, and I fired this thing up, and I learned real quick that this pressure release valve right there does not take much to unseat that. And I hooked up a scope. I actually threaded the end of one of these things to put a pressure sensor in there with a valve. You can see that's what that valve is there. So that this thing would have the ability of flowing some oil, so I wouldn't completely restrict it. And this thing moves quite a bit of volume, and most of it comes out of this little pressure relief right here. And when you actually go through and look at the amount of pressure that this thing generates, it's like 6 psi. In this case, that's about as fast as you can run it, positive duty cycle wise. I've got my little frequency generator at about, tried to get as close to 100 hertz as I could. and I was outputting almost 90 hertz. If you go above 90, the pump will shut off. But this is the pressure that I achieved out of it, basically 6 psi. So this is not a pump that is here to generate a lot of pressure. It's really there to deliver volume and keep the circuits filled with fluid. And now I know, after I coated everything with oil. Okay. So that about covers these outputs, which are mostly solenoids, other than that auxiliary oil pump. So let's kind of look at the transmission control side of things. And we do have, unlike some of the other transmissions that GM has, like their 6-speed, it has an external TCM, which is kind of nice. Now GM puts it in a weird spot. They actually put it near the PCM, at least on the pickup trucks, in front of the left front wheel behind the splash guard. So it seems kind of like that's in a precarious position. But now Ford combines the TCM into the PCM, so they have an ECM TCM in the powertrain control module, and that's mounted on the back firewall, so it seems to be in a little protected spot. One of the things you want to do is check for updates to programming. And here, using the PTS that Ford has, I just put a VIN number in for a F-150, and you can see under the powertrain control module, we do have some updates that are available. And when they're up there, I just looked, this is a kind of a history that you can look at on PTS through Oasis. You're not necessarily going to have that access unless you have the ability of getting into the Ford screen. Now, this little box up here mentions that this information is fairly up to date, but the vehicle might be even more up to date, so you actually should hook up to the vehicle to find out if it had possibly any of these updates done to it. So it doesn't want you to rely completely on it. But it is nice. For this one vehicle and this one VIN number, it lets you know if there are updates available for any one of these modules. Now this is the General Motors side of things. If you want to see if there's a calibration update available for it, there's one of two ways you can do it. I'm not certain if this is still working, but you used to be able to go to acdelcotds.com and you can sign up. It's free to get a user ID, and then you can go under resources, you can go and look up your GM calibration. You put your VIN number in, and then you can go through and look to see what your part numbers are and what updates are available. Now, if that doesn't work, if you just search GM calibration ID, you're going to see a site with the word Opel in it, O-P-E-L, and they don't sell those here in the US, but it lets you, when you click on that link, it takes you to that exact same site where you don't need to have an account or anything like that. You put the VIN number in, and that's where I went to get this. Now, I do have the GM access, so I could always go through the GM software, but I just wanted to let you know that you do have the ability of checking for calibration updates, even if you don't have any paid subscriptions to anything. And when you go through the steps, you can find out if there is any updates available for that transmission. And then when you look on your scan tool, you make sure that you've got the right part number and CVN number for those updates. If you do, then you're up to date. If you're not, well, then you can go through the process of getting an update for that TCM. Now, GM also has, through their programming, this mechanical characterization and virtual matching. And it's a way to program in, when you put a new transmission in, you program in the numbers, or when you put a new part in, like the valve body, you can program the numbers. So it actually looks up to the cloud and pulls whatever information it needs off of its servers to load the proper calibration into your transmission control module. They've got this thing they call a genealogy tree. So when you go through this process, not only are you updating the vehicle, but you're updating the genealogy on the servers at General Motors with the parts that this vehicle now has. So that's good. They have this number called a ton, transmission unique number, and that's on the sticker on the outside of the transmission case. And then they also have a PUN, a part unique number. And that's going to be a number specific to a part, like this valve body. In this case, this is off of their service information. They want you to scan this code using just a generic scanner to get those numbers, and that is what you'll enter. Now, you have other scans and so forth, and they identify do not use those. You'll use this one right here. Hopefully, all this information is clean and able to be used. That's that human readable number. They say do not use that. This is a matrix where they say don't use that one either. They want you to use that QR code right there. There are actually numbers etched under that. I just don't have the ability to read like that without a magnifying glass. Now Ford has a sticker on the outside of their transmission that has the solenoid strategy and the solenoid body ID. So they actually do put their solenoid body strategy on there. It's this number etched right there, starting with 222 minus the L1MP. So it's that 13-digit code right there. They have that etched. And it's the same as what will be on the sticker on the outside of the transmission. Now this little clip has me showing you the process of reprogramming the solenoid characterization on this GM 10L transmission in a 2019 diesel Silverado pickup truck. And this is using GM's MDI, and I'm using SPS, the service programming system. So this is not done through a scan tool. This is done through their pass-through device for programming. So this is not something you're going to find capable with a snap-on or a top-on or any kind of tool like that. You'll actually need to have the tools that you can use to program modules and so forth. Because you're going to be using the MCMV system, that mechanical characterization and virtual matching, and it's going to be looking up to the server for information and sharing data back and forth. So you can see right here, I've selected reprogram and clicking next. It's collecting some information. This is going to go quick because I edited this down. I'm going to scroll down and find the transmission control module. And I'm picking the MCVM. Now I'm going to pick the actual correct transmission. I've got the 10-speed because this TCM is used in multiple vehicles. And in this example, I'm going to use replace the valve body. Now they want that PUN, and that PUN is that part unique number, and I'm using a code scanner to scan the valve body, and that there pulls up my PUN. So that would be the number that I enter in to that box right there. And then when I'm done, and this is the message that it gives you. Now to go in and just do another method here, I'm doing replace the transmission, kind of pretending like I'm doing that. I'm going to use the tag on the side of the transmission to provide the actual ton, the transmission unique number. That's what I was entering up there. And it's characterizing the transmission based off of that. So that's coming with the as-built data. So if you're changing a major part on this transmission, like the valve body or the transmission itself or TCM, you're going to want to go through this characterization. Now Ford does things a little bit different. I'm using their IDS software, using their VCM interface, which allows me to go through and program the transmission if needed, either the TCM or teach the TCM what's unique about the solenoids, what's unique about the valve body or the transmission. So in this case, you can see I've selected powertrain, now I'm selecting transmission. At the bottom, I'm selecting transmission characterization and solenoid. And then these are the options I've got. The top two are transmission characterizations, the bottom two deals with the solenoids. If I go from the bottom up, when I select solenoid bands, no vehicle connection, this is assuming that you're just kind of bench programming a computer. And you can see it jumps right into go ahead and put the 13-digit strategy in there, and that information is going to inform the computer of whatever solenoid bands you've got. Now this option right here is just solenoid bands. It's assuming you're hooked up to the vehicle. I'm picking the transmission that I've got, which is a 10R80, and go to the next page where it actually pulls up the information on the transmission itself. So you can see this is the solenoid body strategy and the solenoid body ID. And you're like, okay, is that correct? Does that match what we've got? And if it does, this is what we see. These are what they've got programmed here. All the different shift solenoids and the line pressure and torque converter clutch solenoid, what band they have and what range they're in. Now, if I go through and select transmission characterization, it's gonna want, okay, well this is only one option here is the 10R80, so we continue on through that. And kind of the duplicate information that we saw before, the transmission strategy and identification, is that all good? Or you want to update that. If you want to update that, because these 5 possibilities right here, we've got a module replacement, maybe a transmission replacement, or a valve body replacement, where we've gone through and monkeyed with internal parts. So depending on what was done, you're going to go through and select one of those 5 options, and it's going to walk you through the process the rest of the way. After you've gone and you've changed the valve body, you've changed the transmission, or maybe the TCM, you're going to want to go through and do a fast learn or a fast adapt. So you can see right here on the scan tool, if I select transmission service fast learn, it's going to go through and operate these solenoids and look at the speed sensors and go through and learn how these solenoids operate to kind of get a baseline or a starting point. If for some reason when you're done and you go through and drive this thing, you still have some weird shifts, maybe not all of them are bad, but one or two are bad, you can go through and enter clutch learn, and you can learn the return spring or the clutch for each of those and just try to hone in on that specific shift. Now in this video here, I go through and there's a little timer, time lapse. This is one of those little curiosity things I had going on where I was like, what are they actually doing? Because the vehicle doesn't move, and I did this on the lift. The vehicle doesn't actually move, but you hear it banging around in shifts. The only thing it really tells you on the scan tool is that there's a clutch air purge going on in the beginning, and then a calibration process or calibration learn going on after that. So just so you know, when we're looking at these solenoids and how they're operating, I know it's kind of weird to look at it because you're just seeing this big block. And the reason why is because these are switching at a very high frequency, like 3100 hertz. And I've got a lot of time on the screen here, so that means there's a lot of switching on and off going on through here. If I see a lot of white through here, that means these solenoids are, for the most part, off. You can consider that. Then when you see these solid blocks like that, that means they're doing a lot of duty cycling, and that's the reason why it's blocked out like that, because the computer screen kind of blends it all together. So right now, the B and the F clutch are mostly on. A looks like it's mostly on too. But definitely the C, D, and E clutch, those are mostly off. So you'll see these things switch in this process, and then you'll see speed sensor changes. That's what these things are. This is my input speed sensor, these are my intermediates, and then these are the output speed sensor. This is like front to rear as far as like, so input, intermediate 1, intermediate 2, and then output speed sensor. And I recorded this, so I actually had three things going on. I got a scan tool, one scope, and then another scope going on here. And I put that timer there to kind of give you an indication of how long this process took. And once again, this is not important for anything that you guys are doing. This is just out of curiosity, what is actually happening when we're doing these adapts, because it's not happening while we're driving down the road. It's all happening in a stall, meaning the service bay. But they're really looking at how these solenoids, when they operate, what happens to the speeds of these parts internally. So to start out, I'm going to initiate this service fast learn way over there on my scan tool. Now there might be some requirements like temperature. And if you're not at the right temperature, you have to brake torque it and get it up to temperature. And that's what I had to do earlier. If you're in the wrong gear, it'll tell you. And then right now it's going through the clutch purge. And if you were to hear that, it would be bang, bang, bang. So every time they turn the clutches on and off, they're doing them all at a time there. All the solenoids turn off and then turn back on, and off and then back on. And you can see the duty cycle even change towards the tail end of that. It's like off and then on, off, then on, off, and then on. And that is, you hear it when it's doing that. People in the shop will be staring at you thinking you're doing something crazy to the transmission. And these are the speed sensors. You can see my input speed. My output speed sensor shows a pulse here and there, probably just from vibrating back and forth. But and now it's going through the drive calibration in progress. So you can see they've purged all the air out of it. Now they're stabilizing this thing, and they're going to be pulsing these solenoids on, and you'll see the RPM change a little bit on these different speed sensors. Probably not the output speed sensor, but every other speed sensor. And although I don't have that fine enough to be able to tell me, when they're trying to turn a solenoid on, I'd be willing to put money on it that they're really changing the pulse width slightly until they see RPM change to kind of give them that threshold of when a solenoid's on versus a solenoid's off. I almost could see that right there. You see that change that's occurring on our intermediate speed sensor 1. So whichever clutch they're manipulating or modulating there, they were probably learning how that clutch operated. There's likely periods where they're just operating it at a steady state to get things to stabilize. You can see right there something changed. I'm starting to get some RPM input on my intermediate speed sensor 2, and my intermediate speed sensor 1 is slowing down. And at the rate of what you're doing that is probably going to correlate to how they're pulse width modulating these solenoids, and they're learning from that. You can faintly hear parts spinning up and down at different points in this transmission, even though you don't feel it. You can see some blips going on here. They just changed the speeds of intermediate speed sensor 1 and 2 quite a bit. Now our intermediate speed sensors 1 and 2 slow down quite a bit. We'll pulse on the input speed sensor, and now we're spinning up our intermediate speed sensors quite a bit. At that point, they said transmission adaptive values have learned. Now when you're done with this adaptive values, you back out of the screen, and if you put this transmission in park and then in drive, it will not move. The D light will flash and you'll think you screwed something up. But the reality is that what you need to do at this point is shut the vehicle off, walk away from it, let it go to sleep, open the door, close the door, let the lights turn off. It takes about 10 minutes. So you let the vehicle sit for about 10 minutes, and when you come back, when it wakes back up and the modules back up, everything's reset, and the vehicle will drop into drive and you'll be able to drive it. So after you do the fast adapt, you need to drive the vehicle and go through a few drive cycles to ensure that the shifts are good. If they're not good, you keep driving it, and if you get to a point where you feel like it's not getting better, you can go through and you can adapt the individual clutches as needed. So base that off of your range reference chart on which clutches are applying when, and go through and do the individual clutch learns for that specific clutch. So Ford wants you to adapt a little differently. They go through this. This is what they publish in their service information, is you go through and clear any DTCs. Obviously, you shouldn't have any DTCs there. And you want to clear your adaptive tables, get the engine and transmission up to warm operating temp, normal operating temp. Then you want to do a light throttle acceleration, say 15% as an example, where you're basically keeping your engine RPM between 13 and 1600 RPM. Let it all the way up shift to 10th gear. You might have to give a little bit more throttle when you get 9th and 10th. And then you want to slow to a stop, wait 5 seconds, then go through this little sequence, shift to neutral, wait a second, shift to reversed, wait 2 seconds, shift to neutral, wait a second, shift to drive, wait 2 seconds, and then go through and do these steps again, basically 3 through 9, 6 times. And that's going to hopefully learn this transmission and get it into an acceptable shift quality mode there. So that was the electrical presentation. Hopefully this stuff made sense for you. These are the videos that are in the series. We've got this main overhaul, and then the valve body pump and auxiliary pump overhaul. The rebuilding essentials is a good one. When you're going through and overhauling this, make sure you got the right parts and you're upgrading this transmission. Torque converter operation diagnostics is kind of an interesting one because of the different designs of torque converters that they have in here. This is where we're at here, this electrical operation. Then the hydraulic and mechanical operation, learn about the piece and parts and how these valves and the valve body work. And then lastly, tuning. I do have the HP Tuners Unlock TCM. So we have a truck, and I've got it plumbed out with hydraulic sensors. And we go through and change some of these tables in tuning, and we see how it affects the operation of the transmission, not only physically, but we also see how it affects it hydraulically. So hopefully you get what you need out of all these different videos. And if you haven't seen any of these other videos, I suggest you go watch them, and I will see you on the next one then.